Hey guys, so I came across a new problem recently that I thought was very interesting and that you guys would like to see. So the problem itself comes from path integrals and quantum processes. It's problem 1.3 in the book on page 6. And what it asks you to do is it asks you to basically prove an identity. So this is the identity that it asks you to prove. It looks a little bit different than stuff that most people that know the Dirac Delta are used to. Like, where is the summation really coming from? And we'll see that it's actually going to be an idea pretty similar to the Dirac cone. I'm not exactly certain if that's really what it is or if it's just behaving a lot like it. But then the next thing to realize is that in the book, he wants you to use an identity for the Dirac Delta that involves signs. And I kept running into barrier after barrier with that. And I kept getting to a point to where I was having to use heuristic arguments just to get to the final answer. And I didn't like that. So what I ended up doing was actually getting rid of the identity he wanted you to use, and I just solved it using complex variables. And one of the big things I did was I took L and I just set it equal to pi. So the thing that we need to do now is we need to make a couple definitions. We need the complex Fourier series of a variable, or sorry, of a function. And we need the Fourier transform of the Dirac Delta. This is the complex Fourier series. One of the things to realize right now is that even though, yes, we can calculate each of the individual coefficients, we don't actually care what those are. We just want to use them for the definition later on. So we pretty much just ignore these and we just move them around in the summations and integrals as needed. And then for the Fourier transform definition of the Dirac Delta, and so this is our Fourier transform definition. So now all we do is we put these identities into our original equation. So now we have this guy. And basically what we do from here is we just move a couple things around real quick. So that now gets us to this form here. And so the next thing we do is we actually perform just the simple integration on this guy. So just a quick note, the whole reason that I'm bringing this inside of the exponent inside of the dz integral right now is because later on, when we use the Cauchy integral formula, it'll make even more sense why I did this in the beginning. But you don't have to. You get the same results no matter what. I just wanted everything in one location so I can just move on and not have to worry about thinking about that later on. So now we're here, and now we're at the point where we start noticing that we have poles, we have complex numbers, and we have a 2 pi I down here. And so that screams to us that we need to use the Cauchy integral identity, or the Cauchy integral formula. Which we know is this guy here. And what we're going to do so this is going to be our function that is actually being integrated over the contour. And these are our 2 points that the integration is being done with respect to. And like I said, we know that we have a pole at x minus y. So then that's how we know that these are our points of integration. Okay, got to erase a bunch of stuff. And I'm just going to go ahead and rewrite over here all the stuff that was in purple, just to make it clear again what's all going on so that there's as little confusion as possible. So, when we plug all this into here, what we end up with is that, so we have this 2 pi over I here, which can come to the outside. And so then we're just left with the integral of everything inside. And so then multiplied by 2 pi I, you see that those cancel out. So now, all we do is we replace x with y. And then we see that this cancels out, and so we're left with the typical definition that we expect to see from the Dirac Delta. So that's a nice little proof of that. But this isn't what the original problem is asking for. The original problem is asking for this summation up here. So the next thing we need to do is we actually need to introduce a second definition of the Dirac Delta. And it's this guy right here that we're going to be using. And so we plug that into here. And here we do our little cavalier thing of we're just going to move some summations around. And then from this point, we have this identity here. And this right here is just, by definition, going to be f of what's inside of the parentheses. And so then we end up with this being just simply we end up with this as our final result, which, when you consider m just being a dummy variable and L equaling pi, it gives us exactly what we started out with. Anyway, I hope you guys find this interesting. I did. I actually spent quite a bit of time trying to figure it out when I was doing it in the real plane as the original author was intending for you to do. But then once I went to the complex plane, everything actually became pretty clear and pretty easy to to solve out and figure out what's going on. But yeah, so here it is. And hope you enjoyed it.